So the next type of equation that we're going to look at are equations called separable equations. So still first order, but generally speaking, not necessarily linear. And we're going to learn a technique for how to handle these ones. So how do you spot a separable first order ODE? Well, the first thing is you notice that it is a first order, so at least up to a maximum of one first derivative. And then the next thing that you'll notice is that you can divide your differential equation up into two factors, one multiplying the other. The first factor will only depend on t explicitly, and the second factor only depends on the function that you're trying to find explicitly. So it doesn't have any t's in it that you can see. Easiest to see if we just have a look at some examples. So if we look at this first case over here, we've got derivative of u of t is sine of t times u squared of t. So notice that our first factor over here is explicitly a function of t, so that's our g of t, and over here we've got a function of u, so we would write this as f of u because there are no explicit t's. We don't know how u depends on t, all we know is that our second factor is u squared. Okay, so this is separable. If we have a look at this one over here, well, you might look at that and go, not separable, but in fact it is, because we've got a little 1 sitting over here. You can think about g of t. That's kind of, it is a function of t, it's just not a very fancy function of t. So this would be our g of t here, and over here, this is our f of u, where we've got sine of u. So this one is also separable. On the other hand, if we look at the equation just below, now if we have a look at this, we might rewrite it as t plus u of t, but notice that we can't turn this into a product of terms that meet the requirements for separable. So it's certainly the case that this is a function of t and this is a function of u, but we can't write it as function of t times function of u. So this one is not separable. Okay, so how do we handle these? How do we solve them? Well, let's look at an example. And once again, there's going to be a little bit of magic in the middle, which I'll talk about afterwards. All right, so what we'd like to do is find the general solution to this equation over here. Let's just check. It is separable because we have a function of t explicitly here, and then we have a function of u explicitly there. Okay, and just terminology wise, so general solution says we're finding the family of solutions. So this is where we're integrating and we're going to get a plus c. So this is going to look at like u of t is equal to blah 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 plus c. It gives us a family of solutions, and then the specific solution we can only find when we get given some information about which of the family we want to pick. So in this case, we want to find the specific solution which has the initial condition that when t is equal to 1, u is equal to 4. Okay, so we'll find the general first, then we'll plug in and we'll find the specific solution. Okay, so we've got du by dt is equal to t u squared of t. And the first thing that we're going to do is we're going to divide through by whatever our function of u is. So in this case, we're going to divide through by u squared. And I hope at this point that your spidey sense is kind of going, wow, alert, alert, because we're making an assumption here, which is that u is not equal to 0, because otherwise we'd be dividing by 0 and then the universe would explode, which is bad. So the thing you need to be careful of here is you are excluding solutions of the form u is equal to 0. So at the end, we're going to have to look and see if u is equal to 0 is potentially a solution, because when we find the general solution, we want to find all the possible solutions. Okay, so assuming u of t is not equal to 0, let's divide by u squared of t. So we get 1 over u squared, and I'm just, for notation purposes, going to stop writing the of t. We know that u is a function of t. du by dt is equal to t. Okay, nothing fancy so far. Now what we're going to do is we're going to integrate both sides with respect to t. So let's integrate okay, so we're going to get the integral of 1 over u squared du by dt integrated with respect to dt, and we're going to integrate this with respect to t. Okay, so this is where the magic bit happens, and again it is based on stuff you learned from Calculus 1. It's based on kind of change of variables, but it turns out that this slightly hairy looking thing over here is in fact equivalent to the rather delightful 1 over u squared du. Okay, so we will have a look at why these two integrals are the same after this, but for the moment, just trust me. Okay, believe the magic. That this integral with respect to t is the same as this integral with respect to u. Okay, and so we're going to do. So now we have two integrals, which are pretty straightforward to do. Let's go ahead and do them. We're not going to forget our constants. So integral of 1 over u squared is going to be u to the minus 1, and we need a minus over there, plus c1 is equal to integral of t is a half t squared plus c2. Okay, but now I have a look at this and I've got two constants that they're arbitrary constants. I can just as well, and they take on any value in real numbers. So I'm going to combine them into a single constant. Well, you can. So that I have minus u1 to the minus 1 is equal to a half t squared plus c. Remember where we're wanting to go with this. We want to have a solution of the form u of t is equal to some stuff just involving t's. So we need to do a little bit of work. So we've got 1 over u of t is equal to minus a half t squared. And I'm just going to do plus c, where I'm just kind of multiplying the original c by a minus sign. Again, it doesn't matter because it's an arbitrary constant. This is the kind of frustrating thing that will often happen when you're working with constants like this. So long as you keep a constant, that's the key thing. Okay, and then finally, let's just flip this upside down. So what do we get in the end? We get u of t is equal to, and I just want to make sure that I've got this correct. Oh, actually, no, I didn't in my notes. So let's be a little more rigorous. Let's keep this minus sign here. I'm going to take the minus sign out, and then I've got half t squared plus c. Did I do that? Yeah. Okay. So here is our general solution. So just like when you integrate, you can get your family of solutions, which is a whole suite of possible things depending on your c. That's the same, exactly the same thing happening here. We've got a general solution. If we want to find the specific solution, we wanted to find the solution where at time t equals 1, u is equal to 4. So we substitute in 1 and 4. So we get 4 is equal to minus 1 over a half plus c. And you can torture yourself with the algebra and you'll find that c is equal to minus 3/4. So our specific solution is that u of t is equal to minus 1/2 t squared minus 3/4. Okay, so that is the technique in a nutshell. If you are wondering why the magic works, So if you're thinking about this bit over here, the idea is that you do a change of variables. So again, it's kind of thinking back to what you want. You can define a function, you can define a new variable that will let you show that these two integrals are the same. I challenge you to do that, or go and have a look on the internet how it's done. It will remind you about Calculus 1 and change of variables. If you have any questions, you can come and ask me. It does work. Okay, so here is the general procedure for separation of variables. It's following the steps exactly like I did. You can work through that, and you can also have a look and see if you can do this reading exercise using separation of variables. Then, as another practice, here is something about quadratic error resistance. So have a read through that and then use separation of variables to solve this problem. And I will put the solution in the final notes. So we've had a look at two different techniques for solving simple differential equations, which work very nicely. But firstly, you can't always solve all differential equations. There are lots and lots which you cannot solve analytically, no matter how many courses in ODEs you do. And secondly, sometimes just getting an equation is not super helpful. Sometimes you want to think about families of solutions, or you might just want to do a kind of quick estimate of what the solution might look like without actually going to the trouble of trying to solve it analytically. And as a result of this, there are many, many ways of kind of getting graphical insights and qualitative insights into differential equations. So you don't actually solve and find the final solution initially. You look at the differential equation and figure out from there what solutions might look like. So that's what we're going to spend the rest of this particular video looking at. So the first technique that we're going to do is direction fields, and if you took a multivariate calculus, this is going to look hauntingly familiar. Okay, so we saw in the problem that I gave you at the end of the previous video, Newton's law of cooling. We saw it in the form dt by dt is kT minus the environment or the temperature. So this says that the rate at which a body cools is proportional to the difference between the body and its environment. We can recast that in a slightly different form. So if we have a look over here, I'm replacing my big T with a U, which is maybe better so that I'm not using two T's. So here I've got my du by dt, and I've again, oh, and I had a minus sign there, sorry about that, because we want it to decrease. And so here's our minus k, nothing's changed there. And I've got my T, my temperature, which in this case is a U. And the only thing that's different here is we're allowing our ambient temperature to vary over time. So it isn't necessarily the case that the ambient temperature stays constant. It might have some sinusoidal variation if you've got an air conditioner that kind of is oscillating or something like that. So we allow that to oscillate. We can do a quick check of what kind of differential equation this is. So we look at it, we know that it's first order because it's only got one derivative. If you rewrite it, you've got minus, so let's have, well actually you'll have plus k a of t minus k u of t. So having a look, this looks suspiciously linear, okay, because we've got our derivative sitting there. This term just has a u of t multiplied by some constant, and this is a term just involving t's. Okay, so it's linear, and in fact it's constant coefficient because these are our coefficients and they are constant. And finally, because we have this term over here, which involves just t's, it's non-homogeneous. So now you know how you could solve these. You would use the first technique that we learned today, so dealing with first-order linear differential equations, and an integrating factor, so the magic e to the minus crazy thing which just works. But let's see what we can tell about this differential equation without actually going ahead and solving. So the first technique, and let's look at a specific version of this equation. So we're going to let our k equal 0.2, and we're going to let our ambient temperature vary sinusoidally. So if we were plotting a solution, so we're trying to find a function u which satisfies this differential equation, and if we plotted that, we would plot it on a tu graph like this. And we can actually build up an idea of what these solutions would look like without solving. So for example, suppose we have a solution that passes through the point t is 5, u is 8. So we're going through this point 5, 8. Okay, so if I had a solution that passed through there, what would it look like on either side? So for values of t slightly bigger than 5 and slightly smaller than 5, what can we say? Well, we can actually say quite a lot, because the thing that we know is that the slope of our solution follows this equation, the one that we've just seen, minus k u of t minus a of t, which in this case we were doing a minus 0.2 u of t minus 10 minus 5 sine t over 2. So we have an equation for the derivative at any point, and the derivative tells us the slope. So if we plug in our t is equal to 5 and our u is equal to 8, then we'll know the slope of our function just at that point. Obviously not everywhere, but at that point. And if you do that, which I did earlier, you will find that our derivative evaluated when t is equal to 5 is 0.998. Okay, so that's useful. What does that tell us? Which is that's approximately 1. So if we look at our function over here, the slope should be roughly 1, something like that. And we know that it's increasing. So we're putting a little line there. And you can imagine that you could do this. So then you might, for example, say, okay, well, I know that the slope at 5, 8 is 1. So now if I go to the point, it looks like I might head towards the point 6, 9, and then I could work out the slope and I could get another slope there. And that actually is how computers numerically solve differential equations. You give them a starting point and they just kind of take little time steps. They work out what the derivative is. They follow the line along there and they keep going. But what you can also do is, mostly we use computers nowadays, a lot more fun if you have a computer that will do it, to just pick a whole lot of points all over and just plot what we call the direction field. So these little arrows give us a direction field, plot that, and we can start to see what the general sort of solutions look like. So here on this side over here, basically a computer has just plotted the value of the derivative at a bunch of different points. And you can start to see, okay, well, supposing I start over here, then my solution will go up, keep going, and you just keep kind of joining the arrows. I'm going to do down, something like this. And in fact, you can get the computer to do that for you too. And so you can start to build up solution curves, as in the second panel on the right. This thing over here with the arrows is called a vector field. Why is it called a vector field? Because each of these little things are vectors. Each little direction thingy is a vector, and it's a field because they're scattered all over the place. We have a field of vectors. So that's pretty useful, particularly nowadays when we've got computers that can do it really quickly, and we will have a look on Friday at actually getting MATLAB to do things like this for us. So this can be a very quick way of starting to see what your solutions look like. Okay, so we can actually go a little bit further than this sort of analysis with a particular kind of differential equation called an autonomous equation. So we've seen all kinds of differential equations. This particular one, type, autonomous, have this form here, where we don't have t mentioned explicitly anywhere. So for our separable ones, we were able to, let's go back here, oops. For our separable ones, we were able to split our differential equation into something involving t multiplying something just involving u. Autonomous don't have the something involving t. They just have u's. You can't see any explicit t's. Okay. So let's have a look at some examples. So here's our first case over here. So this is called the Hill Keller Ode. And if you go and read the first chapter of the textbook, which is just a kind of introduction, it's number 1.3. What does it look like? It says dv by dt is equal to some constant p minus some constant k times v. So there's no t's in there, so this is autonomous. If we have a look at this bunny over here, again, looking at the right-hand side, no t's, okay, only u's. So that's also autonomous. This equation over here, which we will encounter at some point, it's called a logistic equation. And again, you can go back and read the introduction if you want to find out a little bit more about it. It's used for modeling populations which have a carrying capacity. Again, no t's, so it is also autonomous. But this one over here, notice that this term here is an explicit function of t. So this is not autonomous because we have something that actually has t's in it instead of just u's. Okay. What is useful about autonomous equations? Well, it often turns out that, I mean, they're not explicitly time varying. So often if you go into engineering, they won't call them autonomous equations, they'll call them time invariant. And they come up a lot, particularly in engineering. And we can actually tell quite a lot about systems that are autonomous. I mean, obviously we can do a direction field, like we have over here. So here is our Hill Keller, which we just met over there, with p is equal to 11 and k is equal to 1. So this is the ODE that we're having a look at. So notice no explicit mention of t. I mean, v is a function of t, but t itself doesn't appear. So what is happening with an autonomous differential equation is that the derivative doesn't depend on the specific time. It only depends on the function that it is the derivative of. And you can actually see that if you plot the direction field, because if you notice, at every time that we have, so here's time t equals 2 times t equals 6, looking along those vertical lines, your direction field is identical. So your derivatives are only depending on the value of v. So if you look at v of 20, you're getting something that looks like this. So it's always the same for all values of v. If you're looking at 11, then you've got this. So we have no explicit t dependence. Okay, things to notice. What have they done here? Why is this? So you might look and say, why is that black line there? Well, if you have a look at this equation over here, one solution is that if we just put v is equal to 11, this will solve the problem. So if you put v is equal to 11, then what you get v of t is equal to 0. And if v of t is equal to 0, that means our slope is 0, and that's what this line is doing over here. Solution at v equals 11, indicated by this horizontal line. So this is our constant solution, not 0, v11. Okay. And you can imagine looking at this, we're not getting a lot of information from plotting this for a whole bunch of different t's, because this is the same for every t. So what we can do is we can imagine that we're kind of looking at this, this vector field from one side. And what would we see? Well, we'd see a line. And if we mark that as the point 11, then we'd see lots of little vectors pointing down if v is above 11. So we're thinking of this as the v-axis here. So if v is above 11, then we'd see lots of little vectors pointing down. So they're pointing towards 11. And if we looked for values of v below 11, then we'd see lots of little vectors pointing up. So we'd see kind of things like this. And this thing over here is called the phase portrait. So now that I've sketched it, I'm actually going to rub this out, and you can see the kind of nice official drawing that was here originally. So this kind of encapsulates all the information basically that we wanted about what's happening to our function. It doesn't quite have the direction of the slope, but it's going to turn out that we can kind of use our phase portrait in order to go back to that. So for autonomous differential equations, a phase portrait is a very quick way of getting some insight into what our solutions will look like. So let's talk a little bit more about these. So a little bit of terminology. So one thing that you'll find is that if we find a solution to an autonomous ODE that is constant, we call it an equilibrium solution. And that's going to be quite important for analyzing these systems. So up here, we found that 11 was an equilibrium solution. And if you think about solutions that were not 11, so if we think about a solution that started over here, what you'll notice for this situation is that all the solutions over time tend towards the equilibrium solution. So no matter where you start, eventually, if you follow this direction field, you will end up basically at the equilibrium solution. So if you think about what this phase portrait is telling you, it's saying that really no matter where you start, whether you're above or below 11, eventually as a solution you're going to end up at 11, at the equilibrium solution. So not all equilibrium solutions have this, but we'll see that whether you tend towards an equilibrium solution or not is kind of fundamental to the kind of problem that you're dealing with. So there is a lot of information in this surprisingly simple diagram over here. So a few more tips and tricks for drawing phase portraits. So suppose we have an equilibrium solution, so a constant solution for some autonomous ODE. Then remember our ODE is written in this form here. So it's du by dt is equal to some function just of u. And if our function of u is an equilibrium solution, so it's a constant solution, then it must be that our derivative is equal to 0. So we've found a solution which is constant. Sorry, we've found a solution, a u which is constant, so the derivative must be equal to 0. And this gives us a way, so if we substitute the derivative is equal to 0 and the function itself is equal to a constant into the ODE, we can see that f at our equilibrium solution is 0. what does this give us? This tells us that if you want to find the equilibrium solutions, you just look at the solutions to f at all of your equilibrium solutions. And these are going to be, these U stars are called fixed points or critical points for the ODE. Similarly, you can look at your function f, not at one of the fixed points or the critical points, and you can see whether it is bigger than 0 or less than 0, and that's telling you that your derivative is either negative or positive, so your slope is either going down or up. And then you can tell whether your line on your phase portrait is going to point towards the solution or away from the solution, because it will point towards the solution if it's negative and away from the solution if it's positive. Okay, read through this. This is all kind of applying calculus 1 in kind of a nice way. We're going to do an example. All right, so here we have what is claimed to be an autonomous ODE. Let's just check. Is it autonomous? Yes, because we don't have t mentioned explicitly. Could we solve this? That's a chance for you to, is that something for you to think about? So if we write this in our autonomous format, so remember our autonomous ODEs we write like this. So what is our f of u? Our f of u here is u squared minus 1. Okay, so our fixed points are the solutions to f of u is equal to 0. So we want u squared minus 1 is equal to 0. And you can hopefully do that almost in your sleep. So that's u plus 1, u minus 1 is equal to 0. And so our fixed points are minus 1 and 1. So previously we drew our phase portrait going this way, but that was just because it was kind of helpful when we linked it to the direction field. But mostly we draw them horizontally. It takes up a bit less space. So the first trick to do is to plot each fixed point as a dot on a line, and this is our u-axis here. So we want to plot minus 1 and 1. Okay, good so far. Now what we want to think about is we need to know if our solution is less than minus 1, will it be tending towards minus 1 or moving away? So we want to think about what is the value if we look at, for example, f of minus 2. What do we get? Well, that's going to be minus 2 all squared, so that's minus 1, which is 4 minus 1, so that's 3. So if we have a look at our instructions here, in each interval, we know that if we're not at one of our fixed points, either our function is increasing or decreasing. So here we've got f of u is increasing in an interval, draw an arrow in the direction of increasing u. So u is increasing in this direction, so we must be increasing like that. So this says that if you look, if your function solution starts over here, it's going to tend towards the minus 1 fixed point. All right, now let's have a look at values in between minus 1 and 1. So let's just take a simple one. F of 0 is going to be minus 1. So in this case, we've got a negative function, so our derivative is decreasing. So in this case, we will be, we need to draw an arrow in the direction of decreasing u. Okay, so we're going in that direction. And then finally, if we want to look in this region over here, so let's pick, for example, f of 2. Then we've again got 4 minus 1, which is 3. So we will have an equation, we will have an arrow like that. So thinking back to what this would mean for our direction field, this would mean that if we picked a function, if we picked a solution that started, for example, over here, so we're looking at a u that is bigger than 1, what happens to that solution as t increases? Well, as t increases, we're going to move away from -1. So we're moving probably we're moving up and away rather than moving towards 1. Okay. Let's link this. So I want to take what we've just said and see what it tells us kind of graphically. Okay, so we're imagining, so remember what our phase portrait said. I mean, what our phase portrait said over here. So I'm just kind of going to sketch in very gently our phase portrait over here, and we had important points were at 1, I mean at -1, and at 1. Okay, and our phase portrait, actually, let me just do this in blue. Okay, so we had our 1 and our 1, and our phase portrait said if you were bigger than 1, then you're going to move away. If you're in between -1, you're going to move towards -1. Okay. So what can we say? Well, we can say that suppose we are a solution starting, for example, at 2. So time t equals 0, we're starting at 2. What will happen as t increases? Well, we know that if we move away from, so we know firstly that our derivative is positive, so we're going to do a little thing like this. And because we're in this regime over here, we're going to have to keep increasing, so we're going to do something like that. On the other hand, if we think about what could have been happening before then, well, we know that up to this point here, we would have been increasing. But once we must have tended towards the fixed point that we were interested in, because we couldn't cross over here, because from this point over here, we would have been decreasing. On the other hand, if we think about what happens, whoops, so maybe actually I'm just going to show you. So that gives you, that's how the picture gets drawn up. Let's have a look at what the actual picture looks like, and then we can see that we understand it. So this was the bit that we sketched. So notice that this is our important 1 line, and this is our important -1 line. If you happen to start somewhere between -1 and 1, on the negative, if we're thinking about this as t is equal to 0, on the negative t side, you must have been kind of tending towards our fixed point, or alternatively going back, you're tending towards the 1. But on this side, you must be tending towards the -1, because remember we had the, how's this going to happen? Remember our phase portrait, oops. Our phase portrait was this, this, this. So anywhere within here, you must be tending towards the 1. So that's giving us this bit over here. And then if we have a look for points over here, so anywhere in here, you must again be tending towards the 1. All right. So this kind of gives us a way from this very simple phase portrait over here to actually build up ideas of what solutions must look like, sort of as we would from a direction field. So you could, and in fact nowadays it's so quick to draw a direction field, people do, but the phase portrait tells you quite a lot. So we want to talk a little bit more about these fixed points, so the points to which, so you'll notice that we have fixed points. So if you think about a solution over here, it's heading away from the fixed point because it kind of diverges up. But on the other hand, if we look at this solution here, it's heading towards the fixed point. And that kind of makes sense if you look at our phase portrait. This is our one fixed point, and any solutions on either side of it, we know are going to move away from it. But if we have a look at this fixed point over here, a solution that starts on either side is going to move towards it because of the direction of our derivative. So this leads us to a definition which says that if we have a fixed point and all the solutions that start quite close to it stay close to it or get even closer, then we call that a stable solution. On the other hand, if it's not stable, then we say it's unstable. We can be a little more specific about asymptotically, and we would say it's asymptotically stable if all solutions that start sufficiently close approach the solution itself. So the first one is saying that if they start close, they stay close, and then so if they start sufficiently close, they stay close, but they don't end up at the solution itself. So they'll stay close. So you might have, here's your fixed point. Let's do t like this. If this is your stable solution, it's stable because you might have things like this. But it's asymptotically stable if your solutions actually tend asymptotically to the stable solution itself. If not, so if neither of these holds, then we're unstable. Particularly in engineering, asymptotically stable fixed points are called sinks because it looks like everything is sinking into them. Everything points towards them. And asymptotically unstable fixed points are sometimes called sources because it looks like things are pointing away. So if here's a fixed point and, well, an equilibrium solution, and you have something like this, that's an unstable solution. It looks like it's leaving from the unstable solution. And you can get a little more involved in describing these things. So let's have a look at another ODE. So we're looking at this one over here, du by dt is equal to u squared. So here our f of u is equal to u squared. So the only fixed point that we have for this ODE must be the solution to u squared equals to 0, so that's u is equal to 0. So let's go ahead and plot that here. So this is u is equal to 0. This is our u increasing. And you can check for yourself if u is less than 0 or if it's greater than 0, then our derivative is always greater than 0. And you know this because you know what the graph of u squared looks like. So the derivative looks like this, and if you integrated that, which you could do really easily, so you know that it's positive, you know that it's positive everywhere. Do we know that? Yes. So the derivative is positive everywhere. So no matter where we go, our solution is growing. So what does our phase portrait say? It says if you're less than 0, then you're going to increase, but also if you're greater than 0, then you're going to increase. So this gives a bit of a conundrum, because if you're a solution starting on this part of our u, so if you're like a -1 or something, you will tend towards the fixed point, so you are stable. On the other hand, if you're starting for u greater than 0, then you're going to move away, so you're unstable. So what would we call this? Well, in this case, we call this semi-stable. And sometimes the notation that gets used is, in fact, you'd use a little, let's try and make this a bit better. Oops. Okay, so now I've just shown you what was there. We would replace this with a circle half full, which says on this side we're stable, on that side we're semi-stable. According to our definition, though, these fixed points are unstable because not all solutions that start close enough stay close. But it is useful sometimes to know that it's semi-stable because you do have solutions that will tend to your fixed point for on some part of the system. All right. So here is a challenge for you, and I'll put the solution in the final set of notes. Let's just move this up. So here's our logistic equation, and again, go and read 1.10 if you're interested in where it comes from. And sketch the phase portrait and classify the stability of the fixed points. So the thing that you might be wondering is, but I don't know what R and K are. Well, in fact, you don't need to. You can figure it out so long as you know that they're positive. Okay, so we've got R and K are positive. And the other thing that you'll know is because it's a logistic equation and it's generally used for modeling populations, only really bother plotting this for u is greater than or equal to 0. See what you can do, and I will put the solution in the final set of notes. Phew. Okay, so there was quite a lot in this snippet. So we learned how to do separation of variables, which was pretty straightforward. And then we talked a lot about how can you graphically and qualitatively analyze differential equations without actually solving them. So spend some time getting good with these techniques. The final snippet for this week, we're just going to talk a little bit more to clarify when we talk about general solutions, specific solutions, how we can know that we found all the solutions, things like that. But probably take a break now, draw some phase portraits, have some coffee, and come back when you're ready.